bei uns hier auf dem Automatica Forum im Zeichen der E-Mobility. Und wir haben jetzt einen spannenden Vortrag zum Thema Batterie-Recycling. Wichtiges Thema und darüber wird jetzt sprechen Joachim Döhner, Senior Director Global Sales in der Geschäftseinheit Battery bei KUKA und auch Vorstandsvorsitzender der VDMA-Fachabteilung Batterieproduktion. Und er wird auch nachher bei unserem Panel, das um 10 nach 12 stattfindet, wo wir so generell über die Anforderungen beim Thema Batterie, Recycling, Produktion, Montage sprechen werden. Da wird er auch mit dabei sein. Und jetzt freue ich mich aber erstmal auf den Vortrag zum Thema Batterie, Recycling. Bitte schön.
Ja, recht schönen Dank. Freue mich, dass ich heute hier sein darf. Ich habe hin und her überlegt and I finally decided to give the presentation in English because it's put online and then maybe it's accessible to more people. My topic is automation in battery recycling. I will try to give you a more generic perspective on this topic, so I will actually keep the KUKA marketing block included here rather short, but not at zero. So everyone probably has heard the name KUKA, and many may know that we make robots and we love the color orange. What is a little bit less known is the fact that we do not only make products, we also make solutions. We make complete production solutions under the roof of KUKA Systems, and there are some pictures. This is body in white, this is battery production lines and other areas as well. And as a matter of fact, this is not smaller than the robotic business, but it's a lot less known. So if you want to learn more about this, please see our booth. We have some exhibits, some nice 360-degree videos, which give you an impression of what we do beyond selling robots. This is just the overview of the organization. So we have the robotics division, the systems division, and also Swisslog, which is making logistics solution, and we have a separate business unit covering the Chinese market. And that's already it for the marketing block. Except for that, if you order the KUKA characters in the right sequence, this translates into Akku, which is the German word for chargeable battery. So kind of battery is in our genetics already. So this is why I have a lot of fun working on this topic. The battery life cycle is quite complex. It starts with the raw materials, then the cell production. The areas where KUKA is engaged do have the orange frame. So for your orientation, we do have some activities in the cell making. Next is turning the cells into modules. Next is turning the modules into packs. You need a housing for that, which needs to be assembled, requires some welding solutions, but other things as well. Then you need to get these batteries into the car, the installation. We have some solutions here. And then we like to use electrical cars, but it's not a business. Once the car has been on the road for a while, there is the end of life, and then time will tell. Maybe there is an opportunity for a second life before the battery is refurbished. And the first step of battery refurbishment is the disassembly, and then comes the recycling in the narrow sense. And then depending on the outcome, it goes into making new cells, or what is not usable goes into disposal. So that's the battery life cycle. This is a chart from Battery News showing all the recycling activities which have been announced for Europe. So as you can see, in almost every country, there are companies now focusing on recycling battery material. So there is kind of a hype, some increasing activity in the field of recycling. It's gaining a lot of importance. And why is that? This is what I'm showing here. So the first aspect, of course, is sustainability. Yeah, we all want to save CO2, we want to save energy, we want to protect the environment, be very responsible in the consumption of natural resources and in avoiding waste. So this is a very nice ideologic picture. It gives some triggers, but unfortunately this does not make a business case, as reality tells. So the next aspect is availability. The materials that are used in battery production are not readily available in large quantities, at least for today's dominant cell chemistries. You have lithium, you have cobalt, nickel, manganese, and these things. And number one, this is a limited resource in that there are no billions of tons available on the Earth. And to make it even more complex, the access to these resources is also quite limited. Yeah? So for some materials, this material exclusively comes from specific regions. So there is also a strategic aspect. If it's available, we also need to have access to it in order to use it. So in order to avoid dependencies, there is an interest to use what is already available in batteries. To give you just an idea of the, how do I get back here? Of the order of magnitude. When you talk lithium, for 1 gigawatt hour of lithium batteries, you need about 350 tons. For 1 gigawatt hour. A gigafab is 10 gigawatt hours. So it's already some kilotons. And then you are talking several hundred gigafactories around the globe. So you're talking millions of tons. So that's the significant volume, which has not been in the circulation before. So this is a problem. Same for nickel, manganese, and cobalt. About 60% of the battery weight is made up from these materials. So for 1 gigawatt hour, this corresponds to 3,000 tons. So for the demand in Europe by the end of the decade, this is already 3 million tons. And it's a challenge to actually get this material. So availability is a problem. That's more a strategical aspect. And then, like always in business life, unfortunately, cost is probably the dominant factor. So as you can see, some typical figures. These figures are strongly fluctuating because, like any raw materials, this is subject to speculation, like oil prices. But to just give you an order of magnitude, for lithium, going cost is some $50,000 to $80,000 per ton. Cobalt and nickel, equally valuable, around about $20,000 to $30,000 or euros per ton. And then copper and manganese are a little bit cheaper. So if you multiply these figures, the demand and the cost, it makes perfect sense that recycling is a good way to save money, reduce strategic dependencies, and keep material in the circulation. And because this is so, there is regulation. Yeah? If people are convinced it's necessary, the fact that there is a law and it's mandated is even adding more to convincing people that this is the way to go. So there is some regulation currently in discussion, the new European regulation on battery. I'm not going into detail, just to give you a brief overview. This is the structure, so it's a very, very comprehensive piece of work covering many areas. And the most important aspects are establishing through regulation a level playing field, so ensuring that batteries that are used in Europe, it's ensured that all rules apply depending on whether batteries come from North America, from China, from Southeast Asia, or from local suppliers. So this is one key aspect. The second key aspect is enforcing the sustainability spirit, so establishing a circular economy, including batteries. And then the third aspect is reducing the environmental and social impact. Batteries, they sound funny. I just was talking to someone in the recycling industry. He says it's a big problem that for recycling plastic waste, often installations go up in flames because someone was tossing a battery in the wrong waste bin. Yeah, so it's been processed, it's been short-circuited, it's getting hot, it ignites the plastic, so it's really a big problem to keep track of batteries and dispose of them safely. So what is covered in this regulation is actually the complete circle of the battery life, as I was showing earlier. So it starts with the natural resources, it gives some guideline on mining and processing, on battery manufacturing, primary use, second life, and then also end of life and recycling. So it's a very comprehensive piece of work. It's still in the making. It still needs to be translated into national legislation, but it is coming. Yeah, so one aspect is, for example, there will be defined quota for recycled material. Yeah, so you need to use X% of recycled material in the production, which is tricky and causing a lot of discussions, but the spirit, I think, is quite clear. So second life is also usually in the discussion. This picture, I understand there is a video game or computer game called Second Life, so I have some visual which has nothing to do with the contents though. The idea of Second Life is quite appealing. So the idea is, if the battery is no longer good for the originally intended use it for something else, so to extend the usage period. An example would be if the car battery capacity drops below 80%, why not use it for home storage, where capacity is not so much of a problem? So that's the idea for power backups. The benefits are quite nice to look at. So you maximize the use of material and energy investment, CO2 investment in the product by dragging out the use. And then from a business perspective, it's nice you can sell the battery twice. Yeah? First you sell it with the car, and then you sell it as a backup. So it sounds very appealing. It's, on the other hand, not so extremely straightforward because there are some challenges. A battery is not a battery. A battery is optimized for its application. Yeah? So for a race car, you optimize for power. For a passenger car, you optimize maybe for energy. For a power backup, you optimize for cycle stability. So it's not quite obvious if the characteristics from the first use are actually suitable for the second use. So this is one problem, and which limits the possible use cases. And secondly, there is some risk involved because the battery, it's not like an odometer. You have 100,000 kilometers on that engine, so you can judge how good it is. The battery looks the same from the outside, but you don't know for sure what's going on the inside. So by reusing it, you're accepting a certain risk. How good is the battery? How big is the hazard that it may actually not survive 10 more cycles, or it may go up in smoke? So this is limiting, the readiness to really go down that road. And thirdly, a question that is, in my understanding, not really solved as of today is who owns the battery? The battery contains valuable material. Who owns it? Is it the battery manufacturer, the OEM, the customer who buys the car? Who's in charge? And this is so far not really sorted out, so that's kind of the downside. So summarizing that, it's not really clear if that second life will really happen. It sounds like a good idea. A lot of research institutions are engaging here. but I'm not fully convinced whether this will be a relevant volume aspect in the future. So, talking about disassembly. When people talk about recycling, specifically in the automation industry, they actually mean disassembly. The recycling, the shredding, and the electrochemical refurbishment of materials is a different story. So I'll go to the aspect of disassembly. When you look at a typical pack, like we've seen in the presentation before, there are a lot of components. So one simple fact is, the higher the concentration of the materials that you're interested in, the better is the efficiency to actually retrieve that material. If you are diluting copper with tons of aluminum, you will not get all the copper out as easily. So the logical step is to remove all dead freight from the battery. So specifically, this means the valuable materials are here in the cells, in the modules. So the job is in the disassembly to open up the pack, take away the lid, rip out the cables, take out the cooling channels, the plugs, the electronics, and most importantly, the battery housing, which is alone well over 100 kilograms of aluminium. So this is really the purpose of disassembly. The question is always, how far do you disassemble? The best practice today, and probably for the foreseeable future, is to disassemble to the level of modules. And then toss the modules into the shredder, because the modules are built so solidly that it's dangerous to try to take them apart into individual cells. You don't want to rip open a cell because the electrolyte is not a very nice liquid that you want to deal with, so you want to avoid the risk of spilling electrolyte, causing a fire by damaging a cell. So the risk to benefit ratio is unfavorable. So my bet is it will stick on the module level when you recycle battery packs. There is a challenge which is causing a headache. So in the pack design, people are optimizing the pack design, meaning they want to make the pack more robust, cheaper, and lighter. Car weight is an issue. So, and this leads to new concepts such as cell to body. So in the future, possibly, there will be an increasing trend to not have these individual modules anymore that you can take out, but large stacks which are glued into the frame. And once this happens, it's very hard to disassemble that again. But everyone knows that. But that's a problem that comes in 10 years. So everyone is focusing right now on being competitive and building cheap and solid modules. Yeah? And let's have the kids worry about how you deal with the scrap in 10 years. So that's a little bit the challenge for the disassembly. But then again, it's also an opportunity for automation guys to find smart ways to deal with this new challenge. So when you look at the figures, these are some, the charts always look the same. Yeah? It's increasing rapidly, that's the common denominator. The absolute figures, they change from week to week, essentially. So this is the total demand of, in Europe for lithium batteries. So order of magnitude, several hundred, 600, 1,000 gigawatt hours per year is the demand. So in a nutshell, this is what is being produced. When you look at the recycling, so when do the batteries, the completed batteries come back, you will see, oops, this was wrong, the big increase happens 5 to 10 years later. Yeah, because initially, the volumes for recycling are defined by what is called the new scrap, which is the not okay material coming out of cell factories when they are ramping. Yeah, so no one likes to talk about what exactly are the yield rates when you start up a gigafactory, but it's a safe bet and a safe statement. It's a lot more scrap than you would anticipate. Yeah, so recently representative of a big German OEM engaging in battery production said, in the end, when the battery is running very nice and perfect, then 10 to 20% of scrap is a good figure. So you can translate that while you're ramping up, it's a lot more scrap than that, so you have a lot of material that you need to recycle. Obviously, this material comes in electrode material, which is nice, so there are no cables, no aluminum frames, so it's a lot easier to recycle, and this defines the recycling volume in the beginning. Later on, in 5 to 10 years, you will have to deal with the packs coming back. Over time, obviously, every car that is being built, every electrical car, will come back 5 to 10 years later. Yeah, and the production figures for electrical vehicles, they are reaching the millions per year. So in 10 years, you'll have 1 million packs coming back. Each pack weighs half a ton, so it's a handful. So today, where do we stand today? Today, everyone is seeing the problem in the future, and they start to think, how do I deal with this? Basically, everyone is getting their hands on some used batteries and manually disassembling them, and starts to think about how to automate this process for the future. But as the volumes are there is no business case for automation yet. This is just a very brief overview on the fundamental processes. Not to forget, when you have a battery coming back, you need to be sure it's really fully discharged. It may be broken inside, so checking the external terminals may not do the trick. You need to open it and short-circuit it to be sure that it's really safe for disassembly. Then you have the disassembly. You take out housing, bars, cables, and these parts. And then basically you shred the modules. You try to separate the materials falling out of this process. And then you have the electrochemical, hydro, or pyro metallurgical processes to really retrieve the materials you're interested in. So there is some links to some quite interesting presentations that are publicly, openly available. So if you're interested to learn more about these processes, you can look that up here. So one nice study done by the University of Aachen battery lab in Braunschweig, together with the VDMA. This is a quite nice brochure, actually. So we have taken on the job of how do you automate the disassembly. So we have developed a disassembly cell. Basically, this is using 2 robots which have tool changers, and you bring in a battery, and then you start to unscrew. You machine open if the screw doesn't move anymore. You can cut open the lids. You can rip out the cables. You untighten the parts. So there is the huge chain of processes that are executed in the cell. Discharging is one thing that needs to happen before, and very important. You also need to be aware of the risk. A battery is dangerous. It can catch fire. So in the processes, safety for the people and for fire hazard is a must. So we've done some research disassemblies of several different battery types. We've developed this cell. And this is a pilot system which can be used by customers to get experience on how to work with that. When you scale, eventually you'll need to inhale 1 pack every 2 minutes, like you produce a car every 2 minutes. So then you have to scale this production, and we do have in KUKA a concept called the matrix production. This alone would be an interesting talk. You can learn more about this when you come to our booth if you're interested. But it's basically a concept where we have individual cells. We have HEVs, which can be programmed to run from cell A to B and C. So you can scale by duplicating these individual cells. Or you can split jobs between cells, or you can have different cells for maybe the disassembly of different battery variants. So in any case, this is a nice way to scale the production from a pilot installation to a full-blown commercial volume application. So I will not go too much into detail here. It's just showing you can have some common preparation areas. You have some automated transport system which can distribute the jobs and the load between individual cells. And this is about what I wanted to tell given the time frame. So brief summary is, number one, battery recycling is a necessity and it's strategically relevant. Yeah, there was a press release yesterday also in German news saying new production facility for battery material, including recycling. So it's important. Second statement, initially, volume will be dominated by new scrap, which doesn't have the problem of disassembly. The future recycling volumes, however, will be dominated by the full battery packs in 5 to 10 years. And this is requiring disassembly and automation. But it's a problem for tomorrow. So today, it's focused on pilot installation, not on volume applications. In my mind, there is no clear perspective, maybe yet, of whether Second Life will be an important volume application. And problem is that the future battery science do not yet address the need for supporting disassembly down the road. And as much as we love recycling, not to forget, and this is my last sentence here, really the quality of the battery and the time that you can extend as much as possible before you have to go to recycling. This is, from an ecological perspective, the most important aspect. Yeah, so meeting recycling quota by scrapping everything very early looks appealing to meet targets, but it's actually nonsense. Yeah, so I remember my family my father's family comes from East Germany. They had the planning, wie sagt man, Planwirtschaft, so the planned economy. So they had, for example, Marx, the book. They had quota how many books needed to be printed. They had a quota for recycling paper. So the result was quite simple. They met all their quota in printing Marx the Capital, and drove the pallets directly to recycling. So you had two companies meeting their targets, but obviously completely defeating the purpose. So this should not happen in battery. And that's it. I'm here for further discussions if you're interested. Now or later, you have my contact address. We have our booth next door. Happy to talk more about these interesting topics with you.
Thanks.